Hello everyone and welcome to another Leetcode video. Today we're looking at the problem select cells in grid with a maximum score. This was question 3 in weekly contest 413. It was another very difficult question. The acceptance rate was extremely low, I think around 2%. So hopefully this video is helpful and just kind of explains how we can solve this. So the question reads that we're given a 2D matrix grid consisting of positive integers. We have to select one or more cells from the matrix such that the following conditions are satisfied. So no two selected cells can be from the same row, and also no two of the values that can be selected are the same. So we need to have at most one value from each row, and none of the values we pick between rows can be the same. So we want to return the maximum sum that we can get by selecting some cells. So looking at this example, we can see that the optimal way to select here is to select 3, 4, and 1. And we'll see that this satisfies our constraints because we only have one cell selected in each column, and none of these values match. So we have a 3, a 4, and a 1, so all the values that we selected are unique. So let's look a bit closer at this example and see how we can solve this. So I think most people that are used to these kind of problems can probably immediately recognize that this is a dynamic programming problem, right? Pretty common pattern that we see pretty often where we have to make some choice which can affect some later choice. So what are the choices we can make here? Well, if we select, say, a value, say we select 1, we know that means we can't select any other cell in that row, right? So if we make a choice to pick 1, we basically eliminate a row. And we also eliminate every other of the same value, right? So if we pick this 1, we can't pick any of these down here. So we also eliminate our values, right? So we see here that the choices that we make do have an impact on future choices. So this usually means that we have to try out every choice and figure out what is the best. But the big issue here is time complexity. So you'll see that if we try to just do a kind of backtracking, try every choice, we're going to run into a time limit exceeded. So let's see what that would look like. So we would maybe start with 1, say, let's select this 1 and just see what happens. So we select 1, we know that we can't select any other value in this row, right? So it makes sense to just go to the next one. Okay, so now we're on this row. Let's select 4. Okay, that works. Let's go to the next row, select this 1. So we would record this value. This would be 6, and then we would basically go back and backtrack. So we'd still have this 4 selected. We say, okay, we can select this 1, and these choices would actually violate our constraints, so we couldn't even do them, but we'd go back, say we can then backtrack here. We'll try this 3 instead, and then we can try this 1. So you kind of see that we basically would try out every single option. However, this is going to be too slow for us, right? Because we have to basically, for every cell, then try every other cell. Either take it or don't take it, and then recursively go through and do all this. So it would be a lot of work. The time complexity for this problem is a bit complicated, but I believe if we're doing this straight up brute force solution, this would be m times n, right? Because we're going through every single cell in the grid, and then what this would be is 2 to the power of m times n, right? Because for every cell in the grid, we then have to go through every other cell in the grid and make the choice whether to include it or not include it, which is where this 2 to the m times n comes from. So we're still going to do dynamic programming, but we're going to be smart about how we keep track of our states. So let's point out a few key things. So see that the number of rows that we can have is less than or equal to 10. And this is a big sign. So what does this tell us? Well, 10 is a very, very small number. So this gives us a hint that we should use bit masking. And bit masking is basically a way of keeping track of choices that we've made using just a single integer. So how would this work? Let's say we have 5 bits, right? And these will represent rows. So say this is row 0, row 1, row 2, row 3, and row 4. So when we make a choice to choose, say, row 2, right, we would come here and we would say, okay, I've chosen a cell from row 2. So I'm going to update my integer value here and set the second bit. So now this integer would now look like 1, 2, 4. So we'd have 4 as our DP state, right? Then in a later problem, we could say, all right, I'm looking at another value from row 2. Let's check this number and see if the second bit is set. So basically what we're doing is we're using the bits of a number in order to keep track of our DP state and the choices that we've made. So for our rows, we can keep track of the ones that we've set using bit masking, which is a single integer. However, our values, right, the actual values in our grid can be less than or equal to 100. So the maximum bits that we can store for an integer is 64, right? So this is not going to work for our values. So we need to figure out another way to keep track of the values that we are using. So you might think maybe we can use a set, maybe we can use an array, but this might add too much space complexity trying to pass this kind of data structure into recursive calls and doing all this. So we can't really use that. But what we can do is be smart about how we actually choose our values so that we're never going to reuse the same value twice. So what would that look like? So let's actually look at our values here. So what if we put these values into an array? So let's say we start with our highest one. We have 4. This is at position 1, 0. Then we'll have 3. We have 2 3s, so we'll have a 3. This is at position 0, 2. Then we'll have another 3 at position 1, 1. And then we'll have a 2 at 0, 1. So you get the idea. So you'll see what we're doing is we're putting our values and their positions into an array. So how does this actually help us? Well, you'll see we're going to process this array in such a way that we don't actually have to keep track of values that we've used previously, because we're just going to assume that the values that we're currently looking at are ones that are valid and we can use. So what would that look like? So we're going to start with the largest value. And why do we do this? Well, because we're trying to maximize the score, right? And what we can do is either try including this maximum value or just not including it at all. So let's say that we decide to include this 4. Okay, so we'll include it. We'll think that's part of our answer, and then we'll move on to 3. So this is where things get a bit more interesting. So we actually have 2 3s, but remember, we can only choose one of these. So what do we do in this case? Well, we actually want to try out each of these options because we don't know which one's going to be the best for us. So we could say, I know I haven't seen any 3s before. So for all the 3s that I see here, what I'm going to do is use that as my choice. So I can either choose this, right, and have some other recursive tree down here that I'm going to go through. I can choose this, have some other tree down here I'm going to go through, or I can just not choose any of these, which might be optimal as well, and just move on then to 2, right? So you'll see what we're doing to avoid having to keep track of a third parameter in our DP state is not even including the value. We're going to sort the values ahead of time so that we could check the highest values first, and then when we move on to the next value, we'll know that there's no possibility it's been used before, so we can try this out without having to worry about if there's going to be a duplicate or not. So our time complexity here is still pretty bad, but it's slightly better than the pure brute force approach that we saw. So we still are going to go through potentially every value in the array, right? So we're going to have m times n values, and then what we're going to do is for each of those, we're going to make 2 to the 10 choices. And this is because we have 10 rows at most, and we have to decide whether or not to include a value from that row. So basically, for each cell, we're going to have to make this choice of rows. So this ends up being m times n times 2 to the 10, which is our final time complexity here. And we'll see that this is good enough in order to pass these test cases. So let's hop over to the code and see exactly how this works. So the first thing that we want to do is pre-process the array so that it's sorted in reverse order. And we can do that kind of more optimal approach to choosing our value. So we're going to start with an empty array. We're just going to iterate through our grid, And what we're going to do is we're going to append a tuple into that array. And it's going to be the first element is just the value. And we're going to sort by this, then just its row and column value. Then at the end, we're just going to sort it by that first value in reverse order so that the highest value is first. Then this is where we actually define our recursive function. So our base case is if our index is ever at the end of this array, then we know that we've exhausted all our options, so we just return 0. So what we're going to do is have this current index variable, and this is basically going to keep track of the end of the range where all our values are the same. So we're basically going to start at our index, and while we're seeing elements that are the same as the current value that we're on, this current index, we're going to increase this index by 1. And what this is doing is basically getting all of the same integer values so that we can go through all of them and try them all. So for example, if the current index we're looking at, the value is 3, we want to increment this index while the value we're looking at is 3 so that we have the range where all the 3s sit and we can try out all of those. So once we have that, we're going to go through that range. We're going to just take that value from the array that we have, and we're going to do a classic take and don't take dynamic programming approach. So take and don't take represent either choosing the current element or not choosing it. So first, we're going to have our take as float negative infinity, because we don't know yet if we can actually even take this option. So we're going to have it as negative infinity, and that'll just be the default case. So now we're going to check our bit mask. If in our bit mask we see that this bit is not set, it equals 0, that means that we can take an element from this row. So what we're going to do is we're going to take whatever I value we're looking at, that value, and we're going to add it into our take value. And then what we're going to do is we're going to say, okay, well, we've seen now a value from this row. So what we're going to do is we're going to go to current index, which is essentially the next value. So we know that we've already exhausted this value in this row, so we're going to go to the next potential value that we can see. So we go to current index, and then we're going to update our bit mask with that bit now set. And then we have our don't take value. So this is just representing we don't take this value at all. So what we're going to do is say, go to our current index, which is the next value. So if, for example, we're looking at all the 3s now, let's say go to all the next smaller values after the 3, and then our bit mask remains the same. Then at the end, our final answer is the maximum of our don't take, our take, and whatever answer we have found previously. So then we return our answer at the end of this function, and finally, we're just going to call that recursive function. So I know there's a lot here. Please feel free to go back and go over it all again. But let's just submit this and make sure that this works properly. And it does work. So this was a pretty tricky problem, and really the hardest part was figuring out the optimal way to keep track of all our current states and not overwhelm our DP with time complexity and space complexity. So hopefully this made sense and was helpful. If you liked the video, please like and subscribe. It really helps. And thank you for watching.